Okay.
That's awesome.
Thank you.
I'll go call people. So do you have an overall title or?
Not really.
Okay.
No, dark matter in the LHC or something like that.
So continuing with our theme of trying to bring you back to the real world, we have Mariangela and Lisanti speaking about dark matter, the LHC.
Okay, great. Thank you. So my general topic is going to be to kind of walk you through some of the biggest experiments that are running right now. And so in order to do that in a coherent fashion, I'm going to do it under the general topic of dark matter. So the plan is going to be to just start today with a general overview and motivations for models of dark matter, both astrophysical as well as particle physics. One thing I should say is that this topic is going to have us live very much on the interface between astrophysics and particle physics. So we're kind of going to be going back and forth between the two. This should kind of set us up for at least understanding what the starting points are for many of the experiments that are being designed and are being run today. And so once we have that, then we're going to go into one class of these experiments, which are direct detection. Probably get to this tomorrow, maybe today. And then the last set is going to be indirect detection. And we'll also tie in LHC searches at the end. Okay, so yeah, we'll probably get to this on Wednesday, the general idea. But let's start off then with dark matter broadly. And what I wanted to do was to kind of give you a tour of the Milky Way. Let's put this down. So what are all of the different components that comprise our galaxy? The first is just stars. There's about 10 to the 11 stars in the galactic disk. And, well, most of them are in the galactic disk, and some of them are off. And their total mass is roughly around 5 times 10 to the 10 solar masses, which is indicated by the capital M and then the circle with the dot in it. So, like I said, most of these stars are located in the galactic disk. So here's going to be my very simplified artist's impression of this. So here's the disk. So it's actually a spiral, but for now we could just treat it like this. Most of the stars are located in the disk. The disk itself is roughly going out roughly 10 kiloparsecs in radius, and in height roughly half a kiloparsec. And the sun is located roughly 8 kiloparsecs from the center. So we're located pretty far out in the disk, kind of close to the edge. All right, so after the stars, we have the interstellar medium. which is just a combination of gas and dust that kind of is mixed in with the stars. In terms of the total mass, it's pretty negligible relative to the stars. So it makes up roughly 10% of the mass of the disk. And so we're just going to mostly ignore this. Okay. Next, part's going to be the black hole, which is just located at the center of the galaxy, and its mass is on the order of 10 to the 6 solar masses. And the part that we're going to spend, all of today and the next few lectures really focusing on is the dark matter component of the Milky Way. Now, most of the dark matter is in the halo. So I've drawn up there the disk, which is where most of the visible matter is, 10 kiloparsecs in radius. The dark matter halo extends all the way around, much, much bigger than the disk itself. Although it's a little bit hard to characterize the exact radius and mass of the halo, just to kind of give you a sense, it can extend as far as 200 kiloparsecs in radius, and its mass is on the order of 10 to the 12 solar masses. So by far the most dominant component of everything I've listed here. The main influence of all of this dark matter is through its gravitational interactions. So all of the evidence we have for it so far is just based on that, and most of the experiments that I'm going to be talking about are focusing on trying to actually detect it directly in the lab so we can figure out what its particle physics properties are. But just to kind of give you an illustration of what we've been able to learn so far just from the gravitational interactions of dark matter with ordinary matter, I wanted to talk a little bit about rotation curves. And so the idea behind rotation curves is to use the stars in the disk as a way of tracing out the essentially as tracers for the dark matter. So it traces out where the dark matter is going to be. And so in order for the stars in the disk to be a good tracer for dark matter, they need to be collisionless, effectively, right? They have to not really be interacting with each other. And so just as a simple exercise, I want you to take a few minutes and I'll give you a few numbers, but I want you to kind of back of the envelope estimate the time between collisions for stars in the disk. Okay, so the numbers you're going to need is, we'll just take every star in the disk to have the properties of the sun. So the radius of one of the stars is roughly 2 times 10 to the minus 8 parsec, and random velocity of the star you can take as being roughly 50 kilometers a second, which is approximately 3 times 10 to the minus 14 parsecs per second. So yeah, so take a few minutes to do this. Feel free to chat amongst yourselves. I realize you have a lot of lectures over the course of the day, so consider this a nice opportunity to kind of stretch and chat and stuff like that. Yeah, so try this out, and we'll see what numbers you guys find. Does anybody want to shout out order of magnitude number? Order of magnitude. 10 to the what? 10 to the minus 30. Oh, collisions per second. Okay. Time between collisions. 10 to the minus 30 collisions. Okay, that's probably, so I have it in my notes in years, but yeah, that's probably going to roughly end up turning to years. So yeah, the point is that it's actually a very large number. And so you can, in order to get this right, you need to figure out what the mean free path is between the collisions for the stars. So that's going to be 1 over the number density of the stars times the cross-section for the interaction. So the number density is roughly 0.6 stars per parsec cubed. And the cross-section, which is just going to be pi r squared, very roughly, is going to be on the order of 10 to the minus 15 parsec squared. So that gives us a mean free path that's on the order of 10 to the 15 parsec. And then the time between the collisions is just going to be the mean free path divided by the average velocity of the stars. And then just substituting these numbers and putting in here the 50 kilometers per second, you get that the time between the collisions for stars in a disk is roughly 10 to the 21 years. So way longer than the age of the galaxy itself. So for this reason, we can consider essentially the stars in the disk to be collisionless. And we also believe that the dark matter is collisionless because it doesn't interact very strongly. So in many ways, the math that we use to describe the motion of the stars in the galactic disk is going to be really similar to the math that we're going to use to describe the motion of the dark matter, because we can consider both to be collisionless. Okay, so if stars are collisionless, then they are good tracers for dark matter, which means that if we follow their motion, we can learn something about where the dark matter is and how much of it is there. And so the sort of canonical example of this, and probably one of the most robust pieces of evidence that we have for dark matter, are rotation curves. And so the idea here is just to, we have our disk, and we have stars that are orbiting around the center of the galaxy. And from Newtonian gravity, we know that the circular velocity of the star is going to be related to the total mass that's enclosed in its orbit, right? This is just first year physics. So that's the relation, right, for the velocity of the star. So the mass is all of the mass that's enclosed, and this is just the radius at which the star is located. So we can go out and actually just look at the motions of stars that we observe as a function of distance from the center of the galaxy, and we can see how that depends on the distance of the star and the total visible mass that's enclosed. So in terms of the historical context for this, this was first done in the 1930s by Babcock, right? And his measurements were following the first mention of dark matter, which was mentioned in the context of looking at the velocities of clusters in galaxies and noticing that their velocities weren't were not related to the mass that was in that galaxy. So that kind of got, Babcock did this rotation measurement in the 1930s, but the error bars were really large. These are really hard measurements to do. And so, okay, he maybe found hints that there might be something like dark matter, but it wasn't really until the 1970s with measurements by Rubin and Ford, and then also Whitehurst and Whitehurst. So this is, this was the time that these measurements actually got really good, such that we actually believed that they were telling us that there was non-visible matter that's there. So what do they actually see? Well, if I draw this down here, can everybody see that? Or do I need to? That's good? No complaints? Okay, awesome. Okay, so remember, I'm going to draw a little. Here's our galaxy, our disk. There's also, and I didn't draw it there, but close to the center, there's like a bulge that happens to have a lot of stars in it. So what you can see is that when you measure the stars as you move out of the disk, you get an increase and then a decrease for things related to the bulge. So that's essentially, as I look at stars kind of going out this way, I'm including more and more mass of things that are in this bulge. And after a certain point, pretty much right where this peaks, that's going to be the radius of the bulge. And then as I continue doing this, right, so as I continue then going out this way and looking at these stars, I'm including more and more of the disk. So the disk component then looks like, let's do that one in yellow. The disk component will peak a little bit later and then fall off. The fall off is always just 1 over square root of r, just Newtonian gravity, where the peak here is roughly the radius of the disk. Now, if that's the only thing that was there, we would take the sum of these two components, and the thing that we'd observe, I guess I don't have any other color chalk, but would be something that would look like this and then fall off once we look at stars that are beyond the edge of the disk radius. But instead, what's observed is that this is flat out here. So instead, it roughly goes flat. And it's that flat component that's indicating that there's some additional mass that even when we're looking at stars that are out here that are contributing. And so the hypothesis is that if we have a dark matter halo, it starts kinking in with mass here right where the other components of the visible mass are decreasing and should be negligible. So it's really the additional non-visible mass that's there that can explain why the rotation curve is flat. So there's two ways that we can explain this. I've already kind of explained it. Well, there's a dark matter explanation, which is just that there should be more mass there, that there's some new particle or particles there that we're not observing. There's also the hypothesis that Newtonian gravity should be modified. And just for full disclosure, I will spend a few minutes discussing this. So these types of theories are known as Mond. You've probably heard that mentioned. The general idea behind Mond theories is, well, we've measured gravity very well at high accelerations, but not at low accelerations. So in the example here of the rotation curve, the point is that the region of gravity that we understand well is where the stars are accelerating very fast. But as you move out, and the acceleration is slower, we don't, there might be modifications there that we just don't know about because we haven't fully tested the theory there. And so it's just a phenomenological extension here. You just end up saying that Newton's theory, F equals ma, gets modified by some function that is some function mu that depends on the acceleration as well as some scale for the acceleration. So this mu is just some interpolating function, and essentially that when x is much greater than 1, when the ratio of a over a naught is much greater than 1, we want mu to go to unity, and so that way we recover in the large acceleration limit, we're just recovering Newtonian gravity, and then in the small acceleration limit, we're going to want mu to go to x, because that gives us F equals ma squared over a naught. And if the force goes as acceleration squared, then you can get a flat rotation curve. Okay? So there's, the community that's focusing on Mond is definitely smaller than the community focusing on dark matter. Where Mond has had its biggest success is on galaxy scale lengths, so explaining rotation curves within the galaxy. Where it hasn't had as large of a success is at being able to explain cosmological things. Yeah? Well, I mean, you have to do it at very low acceleration, so I don't think you can do it in the lab. Yeah, so most of the tests have been looking at like motions on galaxy scales or galaxy cluster scales and things like that. Yeah? What is okay, well, okay, we can figure it out, right? I don't have the number written down, but I mean, essentially, we need to get this. I mean, this form of the force law needs to kick in right where we see the flattening of the rotation curve, and so, I mean, what you end up finding is that the velocity to the fourth goes as gm a naught. So a naught's going to have to be, the value of a naught is going to be related to the value of the velocity where this is flattened. Yeah. I don't have the number off the top of my head, but we can figure it out afterwards if you want. Which anomaly? Oh, yeah, I'm not so familiar with that. So is it on the order? Yeah, well, we can come back to it later in the discussion or something like that, and then, yeah, discuss it more. Right, so the one area where Mond hasn't provided an explanation yet is in being able to explain things like the CMB. So cold dark matter can explain things like when we look at the temperature and anisotropy in the CMB, right, we get our beautiful spectrum of bumps. The relative heights of the peaks versus the valleys here in the temperature anisotropy essentially tell you what fraction of the matter is baryonic versus dark. And cold dark matter provides an astoundingly good explanation of this. And to date, so far, Mond hasn't been able to explain CMB. So I think if you were to talk to somebody who's like a dark matter person, this for them is really good evidence for why dark matter should be a particle and not a modification to gravity. If you talk to somebody who's more interested in this, they might say, well, we just need to work out the right theory. So far, we haven't, but maybe we will be able to do this. I guess I sort of fall in this camp, and that's what most of these lectures are going to be on, but I just thought I'd at least lay that out there so that that there's, this whole debate hasn't been fully sorted out yet. Okay, so for the remainder of the time today, what I want to do is focus on two questions. The first one is, how is the dark matter distributed in the galaxy? And then the second one is going to be, what is the dark matter mass? And in answering both of these questions, I'm going to give you essentially our starting point guesses, because we don't know what the answer really is to either one of these questions. So I'm going to lay out the arguments that have essentially been used to guide the first round of experiments that we're doing for dark matter. But suffice to say, this is something that's changing a lot. And as we can, as we get null results from these experiments, it's forcing us to go back and rethink a lot of our assumptions that I'm going to, lay out now. Maybe I'll go here now. So first question is, how is the dark matter distributed? And so to answer that, we need to answer two things. What is the density distribution of the dark matter, and what is its velocity distribution in the Milky Way? And so as a starting point for that, we're going to go back and actually just revisit arguments that were in some of the original dark matter papers from the 1980s. So some of these papers, for example, there was Goodman and Witten, who were actually the first to propose the method for directly detecting dark matter. And then their paper was followed up by a paper by Drucker, Fries, and Spergel that kind of developed the idea in a little bit more detail and addressed some of the astrophysical issues some more. So both of these were mid-80s. So what happened was, in the Goodman and Witten paper, they laid out the idea of, well, if dark matter is kind of streaming through Earth and in the galaxy all the time, then at some point it should knock into a nucleus on Earth. So what happens if we build a detector, put it deep underground, and just kind of wait for one of these dark matter particles to knock into one of these nuclei? And they just kind of estimated what the rate for that should be. In the Drucker, Fries, and Spergel paper, they revisited the same idea, and then they said, okay, well, we are going to need, in order to make better predictions for this, a more precise model for what the velocities of these dark matter particles should be and what their density should be near the Earth. And at this point, the only kind of solid evidence that we had, right, was coming from rotation curves. So they said, okay, let's start from that. What do we know from rotation curves? Well, they're flat. A flat rotation curve means that the dark matter mass has to be proportional to radius, right? Because if this is the case, then when I plug in the mass in here, it cancels the factor of radius in the denominator, and then I get that the circular velocity should be independent of radius. And so this is coming from the flat rotation curves. And then that tells me that my density, my mass density for the dark matter as a function of radius is just proportional to mass over r cubed, which goes as 1 over r squared when mass is proportional to radius. So this is, just from measurements of rotation curves, we get a very rough estimate that the density of the dark matter distribution as a function of radius goes as 1 over r squared. Now, it turns out that once we know what this density distribution is, that we could use this to estimate what the velocities of the dark matter particles are. And in order to make that leap, so to tie in from density to velocity, we can make this leap if we make the assumption that the Milky Way halo is in equilibrium. So when I say Milky Way halo is in equilibrium, what does that mean? What does that require in terms of the formation of the halo in general? Are there any thoughts on that? So the halo is forming from a bunch of mergers of smaller halos. Just kind of maybe sketch this out here. So you start off with a bunch of density perturbations. Each one of them continues to grow with time, and you get, this is, over the universe, you get a bunch of little subhalos that are all gravitationally attracted to each other. With time, those subhalos merge, and some of them, let's say, if these ones merge together, you'll grow. So some of the subhalos will grow bigger and bigger and bigger because they've been merging with more of these little subhalos. So in this context, coming back to the question, what would it mean, what would the requirement need to be on the merging history of the Milky Way halo in order for it to be in equilibrium today? Yeah. So you would want the Milky Way halo to have formed a long time ago. That if a lot of these mergers are still ongoing today, that means that that the system hasn't come into equilibrium yet. So the requirement here is essentially that we could say that the last major merger happened a long time ago. Now, it turns out, just generally speaking, that this actually is a pretty good assumption for our Milky Way. The Milky Way is pretty quiescent, so it's not in the middle of any major merger right now, which is probably good for us. Which means that the arguments that I'm going to lay out next are actually fairly accurate, even though there's a lot of simplifying assumptions that have gone in there. Yeah? No, well, those are stars in the disk. Those are stars in the disk. It's different from subhalos merging together. So these subhalos, these are dominated by the actual dark matter that's there, right? So you can imagine it this way. So each of these halos has a small little disk in it, right? So each one of these has a little disk, but their mass is really dominated by the dark matter in them. And so when they merge, the stars and everything get tidally stripped off, but so does the dark matter. And most of the interesting stuff is actually coming from the dark matter that's getting stripped off because there's so much more of it than the stars. Yeah?
When you talk about collisions, you have actual physical collisions between stars. But of course, there's a larger cross-section for some kind of gravitational interaction, which must be happening here when things collide.
So this is going to be a much more complicated type problem, and the best guesses we have are actually coming from n-body simulations, which I'll talk about in a little bit. Yeah, because here you have just n-body gravitational interactions, and it's a much more complicated issue than just doing the simple, collision length that we did for the stars in the disk as well. Yeah. Any other questions on this? Okay. So let's run with this assumption that does this also go up? Yes. Okay. Yeah. So let's run with the assumption that the Milky Way is in equilibrium, and that our one piece of evidence is that the velocity, the rotation curve is flat. So that tells us something about the density distribution. So now, how do we relate density to velocity with this assumption that the system is in equilibrium? And so in order to do that, what we need to use is the collisionless Boltzmann equation. Which tells us how the phase-space distribution changes with time, right? So this allows us essentially to track the phase-space distribution, which I'm going to denote as follows. So the collisionless Boltzmann equation just tells us the following: that if I take the time derivative of the phase-space distribution and then spatial derivatives and then derivatives with respect to momentum, that's equal to 0. So Q and P are just the usual canonical coordinates. And in this context, we're essentially just treating the dark matter as a fluid. So it's essentially just a collisionless fluid, and its motion is described by this equation. And it turns out there's a theorem called Jean's theorem that says that if you have a collisionless fluid, so in this case, it applies to the case for dark matter, and it's in equilibrium, that you can always write down the phase-space coordinates in terms of the integrals of motion. So let's see, phase-space coordinates. So the phase-space coordinates are only going to be a function of the integrals of motion. And just as a reminder, a function is an integral of motion. So I is the integral of motion if its derivative with respect to time is 0. So this equilibrium assumption actually is quite powerful, because it essentially allows us to immediately write down some form for that velocity distribution. For the dark matter. Okay, so one example is the Hamiltonian is an integral of motion, right? Energy conserved. And so by Jean's theorem, I can say that the phase-space distribution for a system that's in equilibrium can be a function, bless you, of the Hamiltonian. I can also consider more complicated scenarios, for example, where the phase-space distribution is a function of the Hamiltonian and angular momentum, or the total angular momentum, or angular momentum in the z direction. That would give me alternate forms, but we're just going to stick to the simple scenario for this.
Is the assumption that the halo does not have a lot of angular momentum as opposed to the disk?
Yeah, so if I do this, the assumption is that the halo doesn't have a lot of angular momentum and that its velocities are going to be isotropic, which we actually think is not true. Because we do have some evidence that the halo is more of an ellipsoid. So think of like a beach ball but squished. So it does have a little bit of an angle to it. The uncertainties on this are quite large because in order to do this, we need to essentially use motions of stars and things like that to get an estimate on what the gravitational potential is of the Milky Way. So that this isn't sort of all set in stone yet. But yeah, so this is probably too simple of an assumption, but it's kind of good enough as a starting point. Okay, so I've just used, so this is coming from Jean's theorem, right? So putting it all together, if I have collisionless dark matter, it's in equilibrium and isotropic. And the isotropic thing is just coming from the fact that I only depend on h and not on angular momentum. Then the claim is that the density that we obtain from the rotation curves, which goes as 1 over r squared, corresponds to a velocity distribution that is just a Maxwell-Boltzmann. Okay, so what I'm calling psi here is just going to be the potential. It's just a shifted gravitational potential. Okay. Okay, so I just want us to spend the next few minutes just showing this exactly. So let's do out the proof of this. So the first step here is that we need to relate the density to the gravitational potential psi. So that just comes from the fact that the number density is going to be proportional to the integral over velocities of the velocity distribution. So if I put in a Maxwell-Boltzmann here for f of v, then I find that the density rho is just proportional to E's gravitational potential over sigma squared. And then the last step is to use Poisson's equation to rewrite this in terms of, well, let's see, to relate psi to radius. So Poisson's equation is going to tell us that del squared psi is equal to minus 4 pi g rho. And right, so this just ends up becoming the following. I'm going to writing this out in terms of expanding the del squared in terms of spherical, doing the spherical expansion. So the problem just comes down to solving this differential equation for rho. And if we do that, we find that rho just goes as 1 over r squared. So for a system that's in equilibrium, that has a density that falls off as 1 over r squared, we see that it's linked with a velocity distribution that's Maxwell-Boltzmann for the dark matter particles that are there. Now, as we've kind of already been discussing, these assumptions are quite simplifying. And for one thing, this is all relying on the fact that the rotation curve is flat. That's what allows us to start off with the assumption that the mass of the dark matter is proportional to radius. If that were the case, if the rotation curve was flat up to infinite radius, that wouldn't actually make any sense. It would mean that our local dark matter halo was infinite in mass. And so that tells us that at some point, the rotation curve must not be flat anymore. We're just not actually measuring any stars that are going out that far. And so at some point, all of this is going to have to break down. And our best guess for how it changes is coming from n-body simulations, which I had mentioned before. So there's a lot of really phenomenal progress. A lot of really amazing progress has been made on this front in recent years. What these simulations do is essentially follow, you give the simulation initial conditions on what the spectrum of perturbations are, density perturbations, and then it just follows the growth of all of the subhalos, and it follows all of the interactions between all of these subhalos, which is a complicated gravitational problem, and then it sees what we end up with today, effectively. And so from very detailed n-body simulations, we find that typically Milky Way-sized halos, so halos that are roughly 10 to the 12 solar masses, have a density fall-off that follows what's called a Navarro-Frank-White distribution. And it's essentially a double power law in radius. So this RS is a scale radius, and it just tells you where you transition from one power law to the next. So very roughly, kind of at small r, your density falls off as 1 over r. At large radius, your density falls off as 1 over r cubed. And then there's a transition point in the middle at the scale radius, which is roughly 20 kiloparsecs, where the density fall off is 1 over r squared, which is isothermal. We don't know why. We don't know where this NFW comes from. We can't derive it from first principles. It's actually kind of amazing that most of the simulations always end up kind of spitting out something that's roughly of this form, but we don't really know. We can't derive it. The other thing to note is that all of the simulations so far, the highest resolution ones, only contain dark matter and don't contain any baryons. And the inclusion of baryonic physics, we expect will actually change things quite a bit, and in particular will change things down here at small radii, where you start becoming very sensitive to what's going on in the disk. Like if you have supernova explosions or the black hole ejecting energy, that could redistribute the energy and the matter close to the galactic center, and it can change this density distribution. For example, it could flatten it out or can make it more cuspy. So that's something that's considerable uncertainty in terms of what's going on close to the center of the galaxy. So that's kind of the layout of our starting assumptions on the dark matter distribution. So we have some rough guesses as to what the distribution of the dark matter is in the galaxy, and some rough guesses as to what its velocity distribution looks like. Most of these guesses are coming just from evidence from rotation curves, and then now from these n-body simulations. And it may turn out that there's a lot of assumptions in this that end up turning out to be wrong. That's something that we're only going to be able to work out as the n-body simulations improve, and then also hopefully with a potential signal. Okay. Are there any questions on sort of this, the starting assumptions on the astrophysical distribution of dark matter? No? Oh, yeah.
I would have thought that's going in kind of what you were at again, because collisions would kind of, that's what happens with a gas.
Yeah, it's actually, it's kind of all related.
But
yes.
But this distribution seems like it's not pure.
Yeah, there's, yeah, it's not. And actually, when you look at the velocity distribution that you get from the simulations, you see that it's not pure Maxwellian, that actually on the tail is quite different of the distribution. And what that's coming from is essentially a breakdown of the assumption that the halo is completely in equilibrium. That's mostly an okay assumption, but it's not perfect. We do know that there are ongoing mergers right now. Most of them are small, because we see dwarfs, and so dwarfs are essentially mergers that are happening now. Most of them are small mergers, but there's probably enough of them that it's kind of messing around with that equilibrium assumption. Yeah. Any more questions? No? If not, then I'm going to move on to our starting assumptions on the particle physics nature of dark matter. So in order to really be able to design an experiment to look for dark matter, you need to have some idea of what its mass is and how strongly it's interacting with ordinary matter in order to have any starting point on estimating what the interaction rate is or anything like that. So what I want to motivate, this is all getting wet. Okay. Is okay, so in the remaining time that we have, I want to just lay out the argument for the WIMP miracle, which has kind of been the guiding force up until now. And I'm going to put it in quotes. So the WIMP miracle motivates weakly interacting dark matter with mass that's roughly on the order of 100 GeV. This general idea has been extremely powerful in terms of motivating searches. A lot of the dark matter searches are really kind of primed to look in this mass range. One of the reasons why this has gained a lot of traction is because many models, BSM models that we believe are well motivated for other reasons besides dark matter, tend to actually also give you a dark matter candidate with a mass in this region. So an example of that is in supersymmetry. You tend to get dark matter candidate, like neutralino is one of the lightest stable SUSY partners. It's neutral. You can get masses in this in this range, and so put together, this actually ends up being a very well motivated place to start looking. Now I've put this in parentheses, which I'm going to revisit again at the end, because I don't want you to take the miracle thing too literally. It's not actually that much of a miracle. And as many of these models are starting to get constrained by current experiments, I think it's forcing us to kind of go back and revisit this and really ask ourselves, wait a minute, how miraculous is this? And how should we start moving away from this initial assumption? But before we get that, we just kind of should outline exactly what's going into this argument for WIMP miracle. So the WIMP miracle comes about by being able to explain what the observed density of dark matter is today, right? So in the early universe, we have dark matter particles that are zipping about. They're in equilibrium with themselves. They interact. They give you standard model particles. Standard model particles interact. They give you dark matter particles. And everything is in equilibrium. But as the universe continues to expand, at some point, the dark matter particles are not going to be able to find each other anymore. And at that point, the equilibrium is essentially broken. And that ends up setting what the dark matter density is that we observe today. So said another way, at high temperatures, we know that the dark matter is in equilibrium. Then, as the universe continues to expand, so as the universe expands, at some point, the interaction rate for the dark matter, gamma, is going to be much smaller than the Hubble rate. And it's at this point that the dark matter particles can't find each other anymore. And so what happens at that point is called freeze out. And that ends up setting the dark matter density today. So I want to actually just do this out in some amount of detail. Yeah, we have enough time. So you can see how this actually works out when put it all into the equations. Whoa. Okay. So this whole process is going to be described by the Boltzmann equation. And in particular, we can write it down as follows. So So A here is the scale factor. Oops. N is the number density for the dark matter. N with the subscript EQ is going to be the equilibrium number density. Sigma V is the thermally averaged cross-section. Cross-section times velocity. Oops. This is the annihilation cross-section for the dark matter, because essentially we're interested in processes where we have dark matter particles coming in, interacting in some form, and then going to standard model particles coming out. And this is in equilibrium initially. A and A bar. Oh, no, this is to the -3. Yeah. Sorry. Yeah, that was a big minus. OK, so it'll be useful to rewrite this in a form that's going to be a little bit more illuminating. And so we're going to go through just a little bit of algebra here just to make that transition. The first step is to rewrite this in terms of temperature. And to do that, we're going to use the fact that temperature is proportional to 1 over A. And then I'm also going to define the quantity capital Y as being number density divided by temperature cubed. And similarly, Y with an EQ is going to be equilibrium number density divided by temperature cubed. And let's see. I'm trying to see how many of these steps I should actually do up here. So the first thing we get by making the substitution with the y is we can rewrite this equation as follows. dy dt equals temperature cubed sigma v y equilibrium squared minus y squared. And the last step is going to be to rewrite this in terms of new variable x, which is going to be just defined as mass divided by temperature. So as temperature increases, x decreases. And when I do that, that's going to give me the final form that will be a little bit more illuminating. So I will write that up here. All right, so what we've got is the following. I'm going to write it nice and big because we're going to spend some time thinking about this. Where lambda is just going to be some combination of mass, cross-section, and the Hubble. So this is the main equation that describes the freeze-out process for dark matter. It actually cannot be solved analytically. It's a Riccati equation, so there's no nice simple form I can give you for this. But in lieu of that, what we're going to do now is just kind of think about this in terms of limits so you can see what happens. All right, so in the case where the annihilation rate for dark matter is much larger than Hubble, lambda is going to be large, and y, which is just a rescaled version of the number density for the dark matter, is essentially going to track the equilibrium expectation for y. Where should I draw this? Okay. So in that limit, where the annihilation rate for the dark matter is much greater than h, the number density for dark matter looks like what you'd expect if it were just in equilibrium. It looks something like that, falls off exponentially. What happens when I go to that limit, where the Hubble rate is now going to be, much bigger than the expansion rate? Well, much bigger than the annihilation rate. Well, in this case, dy dx just goes as minus lambda y squared over x squared, which you can just solve to give you the following. Essentially, this ends up giving you the fact that the number density of dark matter at infinite time is a constant. So that tells us that even though initially the dark matter number density might have been falling off and just tracking what its equilibrium value would have been, at some point it transitions and its number density is flat. The expected number density is going to be flat. Where this transition is occurring at the point where the Hubble rate is much greater than the annihilation rate. So what happens to this line as I increase the annihilation cross-section for the dark matter? Does this move up or does it move down? Move down. Why?
Because you're annihilating more.
Mm-hmm.
So then you expect to have less remaining.
Exactly. Yeah. So as I increase the annihilation cross section, annihilating more. So there's going to be less that's going to be there today. So as sigma v increases, the number density today decreases. Okay? I mean, said another way is that as the annihilation cross-section increases, my lambda increases, and this constant's going to decrease. Okay? So once the number density flattens out, this here, I mean, this is the freeze-out process. This essentially sets the number density that we observe today. And that is something we measure, right? So that's something we get from CMB measurements, first from WMAP, and now with even greater precision from Planck. So we know what that number is. And so from Planck, we know that this is roughly number density today, let's say roughly 0.12 for dark matter. And then from the freeze-out, you can essentially end up rewriting this as follows, so that it's just 0.1 picobarn divided by the annihilation cross-section for dark matter. And I'm going to take this one step further and rewrite the annihilation cross-section in terms of mass of the dark matter and its interaction strength. Okay, so alpha here is just the coupling strength for dark matter with visible matter, and this is the dark matter mass. So once I write it out this way, and we look and compare it to the actual observed value from CMB, that actually points us to some starting point values for what alpha should be and what the mass of the dark matter should be, right? I don't actually have that much wiggle room here. This is 0.12, this is 0.1. This is telling me that alpha has to be roughly weak scale, and that the mass of the dark matter has to be roughly 100 GeV. And this is what I was referring, I mean, this is the Witt miracle. This is, you know, in order to get the right measured value for the dark matter density today, this is why we make these assumptions for weakly interacting dark matter with a mass around 100 GeV. And like I said, this has really been a guiding force in experimental searches for dark matter for the last 20 or so years. But we are left with this question of just how good of an assumption is this? So by staring at this a little bit, can you guys come up with some other way that maybe we can break this Witt miracle? Yeah? You didn't miss it. Yeah. That's actually, I mean, yes. We can write it out like this, and it's suggestive. So okay, so maybe it should be the WIMP suggestion and not the WIMP miracle. But yeah, that's exactly the point, is that what this is constraining is the ratio of these two quantities. It's not necessarily constraining the individual values. And what the WIMP miracle is telling us is just, well, it's nice, like you can actually choose individual values that would be in a region that we can actually explore experimentally, but that there are other scenarios that could very well exist. So for example, the classes of models that, if I use this, oh yeah, this is fine for now. So the classes of models like what you just suggested, those are called WIMP-less models. And so with these models, we can take alpha to be much smaller than unity, while fixing alpha squared over m squared. So these types of models were explored by Feng and Kumar, actually not very long ago. So, I mean, that's kind of the, the obvious one that you can see just by staring at this. But there's other ways that we can avoid the WIMP miracle. So far, everything that I've written down here was assuming that the annihilation for dark matter to standard model was 2 to 2. I have 2 dark matter particles coming in, 2 standard model particles coming out. I can change that assumption. And in particular, if the relic density is set by 3 to 2 interactions rather than 2 to 2, it actually demands that the dark matter mass be much lighter. And in particular, it's roughly on the order of a GeV. These scenarios were recently explored in the context of what's called strongly interacting SIMP miracle, strongly interactive massive particle. So these are SIMPs. Let's see, so this was like 1402, 5143. So this was Hochberg et al. And then Carlson, Machacek, and Hall also had a paper on this. And the last that I'm just going to list here, I'm just kind of giving you a sampling. There's a whole set of different ways that we can move away from the WIMP miracle. The last thing that's people have been thinking a lot of recently is called asymmetric dark matter. And in this case, you actually say, well, maybe using the measured dark matter abundance today is not really the right starting point for for setting the dark matter mass. And maybe what we should be focusing on is the fact that the ratio of dark matter mass density to the baryonic mass density is roughly 5. This is something that's been observed. We've measured it. We don't really know why. Maybe it's pure coincidence. Maybe it's not. And so these sets of theories are work on the fact that maybe this isn't coincidence, and maybe this is what's actually setting the dark matter mass. And for these types of models, typically the dark matter mass is roughly 5 times the mass of the proton, so roughly 5 GeV. So let's see, asymmetric dark matter, we have Nusanov in 85, and then most recently Kaplan, Ludi, and Zurich kind of brought this back in a more modern light. Okay, but one thing I think you can see from this is that this has provided a really good starting point for us. It sets, it is a well-motivated scenario. There are theories like Susie that definitely give us things that fall into this WIMP miracle category, but we can move beyond it, and moving beyond it actually forces us to start thinking about cases where the dark matter mass can be lighter. And I haven't listed scenarios where it could be heavier, but those exist too. And the sort of strategies that you would use to discover dark matter that's this mass range rather than 100 GeV is different. And so it's forcing us to think a little bit more broadly about the kinds of searches we design. Yeah?
Is there a lower bound on the mass?
From the... Yeah. So you do... there are going to be... You can't have the dark matter be so light that it ends up washing out all of the observed structure. That bound is, so you can't actually, hot dark matter, that's usually referred to as hot dark matter, that's pretty much ruled out. Warm dark matter is still, depending on the model, kind of there. There's like a fuzzy region, the borderline exclusion region on the order of keV-ish. So it's somewhere around there. And then you also get some additional lower bound constraints coming from just how closely you can pack in, if the dark matter is a boson, how closely you can pack it into a halo versus how closely you could pack it in if it's a fermion. That's just coming from Bose fermion statistics. It's much below. It'll be more on the order of that limit starts coming in to kick in around keV-ish scales. Yeah? Most of the searches are geared towards that. These models have gained a lot more attention, probably over the last few years, I'd say, mainly coming from the fact that direct detection searches, which we'll talk about more tomorrow, are starting to place some pretty tight constraints on the 100 GeV range. And so people are starting to think, well, maybe that's been the wrong assumption, and maybe we should start exploring other mass regions. Oh, one way to go is like dark matter. Can we actually get that theoretically? And so there's been a kind of more model building in this area more recently as a result of that. Yeah.
Do we have bounds on upper bounds on mass?
Yeah, coming from unitarity constraints. Yeah, but that's on the order of tens of TeV. Yeah. Any other questions? No? Okay, great.
So does the NFW profile apply to halos around clusters of galaxies as well, or is it just for halos around galaxies?
Yeah, people use it also for clusters. Okay. But for clusters, it starts becoming really important to include, because there's substructure. So the NFW profile is assuming that the density distribution is smooth.
Right.
But